The first example we're going to do is we're going to find the vector equation of a line that goes through two given points. These points have x, y, and z coordinates, so we're working in 3 dimensions. So I'm going to write down my general form of my vector equation of a line, and it's the position vector from the origin to any point on the line is equal to the position vector from the origin to some known point on the line plus a scalar parameter times the direction vector of the line. Alright, so I'm given the coordinates of 2 points. I can use either one of them to make my position vector to a known point on the line. So I'm just going to use the first one. My position vector from the origin to this point right here would just be negative 16 and 4 and 11. Alright, so I have my first term in my equation. Now I need my direction vector. I'm not given a direction vector that the line is parallel to, but I know that it goes from this point, in between this point and this point. So I can make B the direction vector, the vector that goes from this point to this point. So in component form, that would be 8 minus negative 16, 0 minus 4, and negative 5 minus 11. And that would be my direction vector. Alternatively, I could have taken negative 16 minus 8, 4 minus 0, and 11 minus negative 5. That would have given me the negative of this B vector. Remember that a line goes in both directions, so it doesn't matter if your direction vector goes this way or this way. It's the same line. So here is an equation in vector form of my line. It's going to be vector R is equal to negative 16, 4, 11, plus some parameter t, that's a scalar, times my direction vector 24, negative 4, negative 16, where t is an element of the set of all real numbers. The next example we're going to do is we're going to find the vector equation of a line that goes through a given point and is parallel to the line we just wrote the equation for in example 1. So it goes through point negative 7, 2. Again, it's in 3-dimensional space. And the direction we're going to get from the equation we just wrote. So remember, the direction vector was this B. If our other line is parallel to this line, then we can use the same direction vector, which was 24, negative 4, negative 16. But for A, I'm going to use this given point. So the position vector from the origin to any point on the line is going to be equal to the position vector from the origin to this point plus some parameter. I'm going to call it S just because it's a different line, times the same direction vector, where S is an element of the set of all real numbers. The last example we're going to do is we're going to find the angle between 2 lines. So you know that if 2 lines intersect or are skew, then there are going to be 2 angles in between them, right? There's going to be this acute angle, which is equal to this acute angle, or this obtuse angle, which is equal to this obtuse angle. You also know that the acute angle and the obtuse angle are supplementary, meaning they add up to 180 degrees. So when you're asked to find the angle between 2 lines, you usually just ask for the acute angle. If you wanted the big one, you could find it from there. Alright, so we're going to find the angle between these 2 lines by using the dot product. Okay? We're going to use the dot product to find the cosine of the angle theta that's between the 2 lines. So let's write down our formula. The cosine of angle theta is equal to the dot product of 2 vectors, so column V and W, V dot W, divided by the product of the magnitudes of those vectors. Alright, so we know we're going to use this formula. We need to figure out a couple things. First of all, if we're finding the acute angle, remember an acute angle is an angle less than 90 degrees. If the angle is less than 90 degrees, then its cosine is going to be positive. So we're going to do the absolute value of the dot product. That's going to give us a positive value for the cosine of theta, and that's going to give us an acute angle. And the other thing we need to figure out is what we're going to use for V and what we're going to use for W. So what we want is we want the angle between the lines, and that's going to be given to us by the directions of the lines. So the V and W we're going to use are the direction vectors for the lines. So V, we're going to use 6, -4. And W, we're going to use 2 and 3. So then the cosine of theta is equal to, cosine of theta is the dot product of these two vectors, so 6 times 2 plus -4 times 3. And it's going to be over the product of the magnitudes of the vectors. Whoops, that's the absolute value up here. All right, so when we calculate the numerator, we see that it's 0, so we don't really need to calculate the denominator, but I'll do it anyway just for practice. So the magnitude of vector V is going to be root 36 plus 16, and the magnitude of vector W is going to be root 4 plus 9. So we see the cosine of the angle between these two direction vectors is equal to 0 because the dot product of the direction vectors is 0. That tells me that the angle between these two lines is equal to 90 degrees because the cosine of 90 degrees is equal to 0. If we think about the slopes of those given lines based on the direction vectors, for the first line, the direction vector tells us every time we go over 6 in the x direction, we go down 4. So over 6, down 4. That means the slope of this line, which I'm going to call M, because it's the rise over the run, this is the rise because it's the y, so it'd be -4 over 6. The slope of the second line, this is how far we go over. We go 2 over and 3 up. So the slope, the rise, 3 over the run, 2 is 3 over 2. And if we look at these, we'll see that the slope of line 1 and the slope of line 2 are negative reciprocals of each other. So we know that L1 is perpendicular to L2. And that's why when we calculate the angle between them, we got 90 degrees. In this example, we have a line that passes through 2 points, and it's in 2 dimensions. We're going to find an equation of the line in vector form, and then convert that to parametric equations, and finally the Cartesian form of the equation of the line. So we're going to start out with the vector equation of the line. Okay, and that would be the position vector from the origin to any point on the line is equal to the position vector from the origin to some reference point on the line plus some parameter times the direction vector of the line. Because we have 2 points, we can use either of them as point A for the position vector to point A. So I'm just going to use this first one right here. So I'm going to have R is equal to 6, -6 plus the parameter times the direction vector. For the direction vector of the line, I'm going to use the vector that goes from one point to the other point. Remember, it doesn't matter which one I subtract from which because a line goes in both directions. So if I have this vector or this vector, it doesn't matter. It's still the direction of the line. So I'm going to do 10 minus 6 and 2 minus -6 for my direction vector. So my direction vector is going to be 4, 8. If I would have done it the other way and got -4 and -8, that would also be an equation or direction vector of the same line. So now I can put this together. R, the vector R, is equal to 6, -6 plus my scalar parameter times my direction vector, where T is an element of the set of all real numbers. So that's the vector form of the equation of the line. For the parametric equation, I'm going to split this up into my x and y. So remember that r is equal to x, y. So I have xy is equal to 6, negative 6, plus my scalar parameter times my direction vector. Then I can write an x equation. X equals 6 plus 4t, and y equals negative 6 plus 8t. And these are my parametric equations of the line. Finally, I'm going to write a Cartesian equation of the line, and I'm going to do it by eliminating my parameter. Remember, my parameter is the scalar, which is t. So to do that, I want to solve each of these equations for t. So for my x equation, I'm going to have x minus 6 divided by 4 is equal to t. And for my y equation, I'm going to have y plus 6 divided by 8 is equal to t. Then I can set these equal to each other because they both equal the parameter. And I have x minus 6 over 4 is equal to y plus 6 over 8. And I can rearrange this to get it into general form or slope-intercept form. So I can just cross multiply. I'll have 8, x minus 6 is 4, y plus 6. So 8x minus 48 equals 4y plus 24. If I want to get it into general form, I'm going to have my x and my y on the same side. So I'll go ahead and do that. I'll move this one over here. So I have negative 4y plus 8x. And then I want to add 48 to 24. Put it over here. Okay. And then each of these are a multiple of 4. So I can divide everything by 4, or I can just leave it like this, because it's fine. So that is my Cartesian form of the equation. So I have one line, and I have the equation in Cartesian form, which is normal, plain form. I have it in parametric form, which is 2 equations, one for the x-coordinate and one for the y-coordinate as a function of the parameter t, and I also have it in vector form.